Hey, this is Horner. We're going to look at 17.3 and 17.4. The relationship between electric field and potential is 17.3, and it starts off with equipotential surfaces. So if I draw a field line sketch, remember if we had a positive and a negative charge, we always go away from the positive and towards the negative, and we can draw those field lines based on the forces and the magnitude of the forces and where they go. So there's our little field line sketch. That's pretty easy to do. To really see electric potential, we can create something that's analogous to a contour map. So an equipotential, surface has the same potential at every point on the surface, and you're going to see something really cool here. You can actually do this in the lab using a multimeter and using some current that goes across or in between a couple of different charged items. So here's an equipotential surface, something that would look like an equipotential surface. This is called a topographic map, and this shows where the elevation is the same. So wherever the numbers are at, those tell you the elevations, and you can kind of imagine then what this would look like in 3D. So an equipotential surface really here is perpendicular to the electric field line at all of its points. So if you want to draw these using electric field lines, we have to make sure that your two lines are perpendicular. So for example, if I have a positive and a negative charge and I'm drawing my field lines from one to the other, so I do it like this, and we'll show you a really quick equipotential line. The equipotential line would go perpendicular to each one of these. So notice that the equipotential lines here are actually kind of curved a little bit as we get closer and closer to the different charges. There are things called gradient points, and they point in the direction of the maximum increase of potential. And so the negative gradient, that's the electric field, points in the direction of the maximum decrease in potential. For the next thing here, this kind of compares a lot of these different quantities that we've looked at. So for example, our vector quantities are electric force and electric field. If I have electric force per unit charge, I get electric field. And the negative gradient of the electric potential energy is the electric force. The negative gradient of the electric potential is the electric field. So it's just kind of how all these things are related. Big thing to remember is that EPE, electric potential energy, is a scalar, and so is electric potential, but the electric force and the electric field are vector quantities. And this is a kind of a nice summary slide for all those different things. Equipotential surfaces, if you draw them so that the potential difference between adjacent surfaces is constant, then the surfaces are closer together where that field is really strong. The electric field is going to always point in the direction of the maximum potential decrease. So here we go. These lines are electric field lines. So the green ones, these are field lines, and then the circle here that you see, and then the next circle, and you'll see how the circles get closer and closer together. Those are equipotential surfaces, and as they get closer together, they get closer to that charge. And you'll notice that the voltage or the potential as you get closer to the charge increases, and you can see how the lines are really close together. As you get the lines further apart, then that's where you end up with a smaller potential. So really kind of a nice combination between electric field and electric potential. Example 17.11 says sketch some equipotential surfaces for 2-point charges. So to do that, we simply just draw the 2-point charges and then draw the field lines, and then wherever we have the field lines, we can draw nice connected lines that are perpendicular to those field lines. So as we continue to do that, you start to see how those equipotential surfaces will make a circle around each one of our charges. So really kind of a cool thing to see. For the next part, this is the potential in a uniform electric field. So let's say that I have a couple plates and I have an electric field that's pointing to the right. So if I have the two plates here, there's my two really sloppy plates. Remember, it always goes from positive, so positive on this side, to negative on this side. You'll notice those field lines are going from left to right. And if we draw some perpendicular lines, then we can see what happens to the voltage as we go across. So here the potential decreases from one plane to the next in the direction of the electric field. So as you go from the positive end to the negative end, you should have a positive potential and then a negative potential. So really, really nice relationship between the two. Same thing, the potential lines, you'll notice that they are equally spaced apart here. You don't have them all of a sudden all together and then really far apart. They stay at the same distance for those two parallel plates. There's a quantitative or a number way to look at the field strength and the spacing of those lines. So the work done by the electric field, remember we said, is the force times distance. So that force is Q times E. So the charge times the electric field times the distance. And then our change in electric potential energy then is just negative QED, because here we've got work going out. So from the definition to potential, the potential change, or our change of potential, is the change of potential energy per unit charge. So that's just ED. So V is equal to E times D. And this equation just tells us that the SI unit for electric field is a Newton per Coulomb or a volt per meter. Where the field is strong, we'll see those electric equipotential surfaces are really close. And they'll have a large number of volts per meter, and it doesn't take any meters to change the potential in a given number of volts. For a potential inside of a conductor, we learned that the electric field is equal to 0 at every point inside a conductor. Okay, so if the electric field is 0 at every point, then the potential doesn't change as we move from one point to the other, because if there were potential differences within that conductor, then those charges would move in response. So positive charge would be accelerated by the field towards the region of lower potential, and negative would be accelerated towards higher potential. So if there's no moving charges, the field is 0 everywhere, no potential exists within the conductor. So therefore, an electrostatic equilibrium, every point within the conducting material must have the same potential, and it doesn't have to be 0. So we did say that the electric field inside of one of these is 0, so here's our electric field. But everything, or all the points inside, would have the same potential, okay? And there's no electric field on the inside. And that's kind of what it's saying. For 17.4, we're going to switch over and talk about conservation of energy for moving charges. So when we have a charge moving from one position to another in the electric field, there's a change in that electric potential and that in the electric potential energy, and it's got to be accompanied by a change in other forms of energy. So if there's no other forces that act on a point charge as it moves in an electric field, we can say the sum of the kinetic and electric potential energies are the constant. So just like when you throw a ball up in the air, when it gets to the top, it's all potential energy, and then when it falls down to the bottom, when it gets to the bottom, it's all kinetic energy. So we're going to do the same thing, but we're going to do it with all of the electric energies that we've looked at. So changes in gravitational potential energy are negligible. Okay, so when we compared with the changes in electric potential energy, and it's because, remember, the gravitational force is really, really weak when we compare it to the electric force. So here we've got an electron gun. Electrons accelerated from the cathode towards the anode, and that's at a higher potential than the cathode. So the anode has got a higher potential. If the potential difference between the two is 12,000 volts, they want to know what speed do the electrons move as they reach the anode. We're going to assume that the initial kinetic energy of the electrons as they leave is really small, so it's almost 0. So here's kind of what's happening. We have an electron. It's moving from the cathode to the anode, and it moves opposite of the way that you would have a proton. Remember, proton would start here and move the opposite way. So they want us to go through and kind of look at it. We can use energy conservation here. We know that we can set the sum of the initial kinetic and potential energies equal to the final kinetic and potential. And the initial kinetic is 0. And once we find that final kinetic, we can solve for the speed. Here's our equation. We know that the change of potential is equal to the final minus the original potential energy. But remember, we said that's also equal to the charge times the change of potential. So let's go ahead and use our conservation of energy equation and rearrange it for final kinetic energy. That means that we're just going to subtract UF from both sides, and you'll see that here. And now we've got just Ki, so that's your initial kinetic energy minus the change in potential. So here's our change in potential, which we said was Q times delta V. But we said that the speed for this was really small. So K here is essentially equal to 0 because our velocity is essentially equal to 0. And so if we plug 0 in for Ki, we've just got negative Q delta V. Our final kinetic energy, so this side of the equation is 1/2 mv squared. So now we have 1/2 mv squared is equal to negative Q delta V. And we can now just solve for velocity, multiply both sides by 2, divide both sides by m, and then take the square root. We know that the velocity of our charge, as long as there's conservation of energy here, should be equal to the square root of negative 2 times Q times the change in voltage all over the mass. So let's go ahead and take a look at what happens here. We have to have an electron. If we don't have an electron, we're in trouble because now we'll have a negative under the radical, which gives us an imaginary number. So we're glad that our charge is negative. Mass of an electron from the chart is 9.109 times 10 negative 31st. And so now we're going to plug in negative 2, so there that is, times our charge on our electron, which is negative, which is good, times 12,000 volts was our change in potential, and we're going to divide that by the mass of the electron, and we see that the electron's moving pretty quick, about 6.5 times 10 to the 7th meters per second. And that is the end of 17.8, that example. The next section that we'll do is all about capacitors.